hear me now?
Yes, ma'am.
Okay. So last time we spoke about the gauge problem, and there we talked. We also derived the Hamiltonian in a magnetic field, and we evaluated some of the terms. So now today I also want to go back to the Hamiltonian and distinguish the diamagnetism and the paramagnetism in the context of quantum mechanics. So that is, so it's not so mathematical today. So let's see. Let's talk about dia and paramagnetism. So this is what more or less everyone is familiar with. And there is, so diamagnetism is when an object is repelled in a magnetic field, and paramagnetism is when it is attracted to the magnetic field, which means that a paramagnetic system will move in the direction of the field, and a diamagnetic object will move opposite to the direction of the field, if we're talking classically and for translational motion. Now, when it's a molecule, then of course there are many interactions inside the molecule. So you will always have some sort of competition between dia and paramagnetic interaction. Okay, so for example, the interaction of the spin of electrons and nuclei, they will always be paramagnetic. They will want to go towards the field. But there are overall, we will see sort of charge cloud interactions which are diamagnetic, which are repelled by the field. And for different molecules, eventually one or the other wins. So we have to look at that closely. So why which one wins, and then sort of justify how a full molecule is either diamagnetic or paramagnetic. Okay. There is also, of course, ferromagnetism, but in the context of molecules, that does not come into the picture because that is a macroscopic property. And it is a ferromagnetism deals with long range order in solid systems, etc. So it's much more complicated as well, and it involves an arrangement of particles which is not there in a individual molecule. So here we are only talking about dia and paramagnetism. So the Hamiltonian that we had written before, so I'll repeat that once more. So that's this one, pi squared by 2m minus E phi. So if you don't have an electric field, you can forget about, so this was a free particle, by the way. Okay, we wrote the full one here. So this is the molecular Hamiltonian in a magnetic and electric field. Now we will ignore the electric field, okay, just magnetic field. So you have the kinetic energy of the electrons. Okay. Then you have this is the electronic Hamiltonian. So if it was the molecular Hamiltonian, you would also have the kinetic energy of the nuclei and the repulsion between the nuclei. So those two terms would be extra here. This is the electronic Hamiltonian, I should say. Molecular electronic. And you have the kinetic energy of the electrons. Then you have the electron nucleus interaction. Then you have the electron-electron repulsion. And these together, we can call the zero order Hamiltonian H0. So something that does not involve the magnetic field. Then you have the interaction of the vector potential with the momentum of the electrons. That is a first order term. And we've said we're forgetting about the electric field, so we forget about that. And then we have a second order term which deals with the square of the vector potential. And we haven't included spin here. So from here, I can write this as H0 plus E dot P. So I'm getting rid of all the constants in front just to simplify things. So let's say simple representation A dot P. Then I have a half A squared. So this is actually what you would get if you went over to the to atomic units. So in atomic units, you just say E equal to 1, M equal to 1. So then you can get rid of the E square by M's or E by M's, and you only have the numerical factors. So today I'll start from this form, H0 plus A dot P plus half A square. H0 H0 plus A dot P plus half A square. Now, if we had spin, I'll just write it for 1 second. There would also be a B dot S term. So that is the direct interaction of the total spin of the system. So the total sum of all the spin quantum numbers of all the particles in the molecule, dot product with the constant magnetic field B. Or, well, not necessarily constant, any magnetic field B. But we would ignore this one. So let's see. So we are going to open out the A dot P term. So we're using the Coulomb gauge, and we're talking about a constant magnetic field B. And this also we saw last time, that then we can write the vector potential as half of B cross R minus O, where O is the gauge origin. Then I can write this in a little bit of a short notation as half B cross R0. Fine. Then A dot P is basically half B cross R0 dot P, and this is a what is it called? It's called a scalar triple product, right? If I remember, this is called a scalar triple product, and here you can cycle the quantities, and they still are the same. So I can write this as half B dot R0 cross P, and R0 cross P is also the angular momentum of the system with reference to the point O, which is also the gauge origin. So here we identify L0 equal to R0 cross P. And this is and L0 is also the angular momentum quantum number of the whole system. Okay, R0 cross P. But this is the operator form, of course. So we get this. So the first order magnetic interaction of the electrons with the vector potential is basically an interaction of the orbital angular momentum. Now we are writing orbital specifically because we want to distinguish it from spin angular momentum. So orbital angular momentum with the magnetic field B. Here we have assumed a constant magnetic field, remember. Okay. So this is one interaction. This immediately tells you that the first order interaction is of the field with the electrons is due to its orbital motion. Then let's look at the other term, which is A0 squared. Okay, so I can call this A0 just to tell you that I've taken the gauge origin to be O. So A0 squared. So what is this? So this is half B cross R0 squared. This is 1/4 B cross R0 dot B cross R0. So this is again a vector identity, the dot product of two cross products, and that is B squared R0 squared. And here, okay, I'll say that later. And this is the vector dot product with R0 squared. So here B square is basically a modulus square of the full vector B. So I have not put the vector sign. So I could maybe write it even more clearly. So that. Okay. So what do we see here? So here we have some sort of square term which interacts with the size of the system roughly. So R0 square, if you consider the, let's say the average, the distribution of R0 square or the average R0 square for the full molecule, it sort of tells you roughly the size of the molecule in a way. So when we take a particular field, it will become clearer. And this A0 squared interaction is then related to the size of the electron cloud. So it's a interaction of the full charge cloud with the field. And this it's an A square term, so it's always positive. So this in the Hamiltonian, so it's plus half A square. So it's always positive in the Hamiltonian, and it will raise the energy of the system. So this is what identified as the diamagnetic term. Now, so let me write that. So this is the magnetic term, and the interaction with the orbital angular momentum, that is not necessarily so that is 1 second. So that can have both roles. I mean, they can sometimes raise and sometimes lower the energy of the system. So in case there is a paramagnetic contribution, it will come from this one. Okay. So the square term is always diamagnetic. So let me just give me 1 minute. Okay, so I can so I want to clarify just one thing. So this can either raise or lower the energy, but as an operator it is called the paramagnetic operator. So just be careful over there. In case there is a there is a paramagnetic contribution, it comes from the A0 dot P term. So it is called the paramagnetic operator. But it does not necessarily lower the energy. It may raise or lower depending, of course, on the value of the orbital angular momentum. So if I consider orbital by orbital, for example, a p orbital with ml equal to +1, the energy of that orbital will get raised, but a p orbital with ml equal to -1, that orbital will get lowered because of this term. And if ml is equal to 0, it will be unaffected. So this term can have all kinds of signs. It can be plus, minus, or 0. Okay. Then this is this. Then let me do an example of a magnetic field. So let's say I have a uniform magnetic field in z direction. Okay. Then what does my Hamiltonian look like? So I have H is equal to H0. That remains the same. Then I have a B dot L0 term. So half B dot L0. So my field is now, let's see, the B vector is 0, 0, B. So this is half B LZ. Okay, so there's a dot product. And then I have a half A0 square term. So that's 1/8. And then I'm looking at this term. So what's B square? The modulus of B square, it's just B square. R0 square is, so okay, and I'm also setting the gauge origin as 0, 0, 0 for simplicity. This is B square, so x square plus y square plus z square. And then I have minus of B dot R0. So B dot R0 square. Here I only have the field in the z direction. So I have B z square. So that simplifies to H0 plus half BLZ plus 1/8 B square x square plus y square. So the z square term gets cancelled. B square z square term. Okay, so this is now simplified, and I have some. Then I have of some like explicit terms. So let's see what happens. So the paramagnetic term now. So this is a field in the z direction. It interacts with the angular momentum in the z direction. So orbital by orbital, we know what this value is. And then when you take a sum over all the electrons in all the orbitals, you will get a net result. Okay. Now the diamagnetic, this also splits energy levels. So like I said, if you have 3 occupied p orbitals in the ground state, then once you apply a field in the z direction, your the 3 p orbitals will split. So remember that in the zero field, when you solve the hydrogen atom Schrodinger equation, you get basically 3 p orbitals, p0, p plus 1, and p minus 1, which are the, so 0, 1, and minus 1 are the ml eigenvalue quantum numbers. But then because you want the orbitals to be real, you take combinations of these p0, p plus 1, and p minus 1 to get px, py, and pz. Okay, but once you apply the field, then it's the identification of P0, P plus 1 and P minus 1, that becomes clear because it is these orbitals which split and they are complex. So the XYZ loses its significance. So once you have a molecule in a magnetic field, then the p orbitals that you get, you can no longer get px, py and pz from them. They are the p0, p plus 1 and p minus 1 orbitals. And p0 remains the same as the original p orbitals. It's not affected in this case. P plus 1 will be raised in energy and p minus 1 will be lowered in energy. Okay. So you have a splitting of energy levels. So I can say that maybe if you have two p orbitals or three of them degenerate, then when I apply a field, the BZ field, then I split into 3, which is 2p plus 1, 2p0 and 2p minus 1. This set you can represent either as p plus, p0, p minus 1 or px, py, pz. But here you cannot have px, py, pz anymore. They've become complex. Okay, so this term splits energy levels. Now this definitely the diamagnetic term. So this is the orbital paramagnetic term. This is the diamagnetic. Okay, so in the diamagnetic term, it's obvious everything is squared, everything is positive, so it raises the energy. But look at but there's something very interesting here. So any molecular system tries to reduce its energy in whatever situation you place it. It wants to be stable, right? So, and then when you put it in a magnetic field, this diamagnetic term is destabilizing it. But the molecule has something in its hand to adjust to this field. So this x squared plus y squared, that part it can adjust. It can adjust the distribution of its own electrons. So what it does is it reduces the extent of the x squared plus y squared. So what I mean is that the molecule gets squeezed in a direction perpendicular to the field. So if you only have a field in the z direction, like in our example here, then what the molecule tries to do is it tries to reduce the expectation value of x squared plus y squared, which means that it reduces the cross section. So if you have a atom, okay, and you have a z direction, and you put a field, then it gets then it becomes something like this. So it gets squeezed. So reduces the expectation value of x squared plus y squared. So the diamagnetic term squeezes molecules. So it also reduces symmetry in that sense. Okay. So what physical effect is it? So I can see that this is a diamagnetic term and it's positive. But unlike the orbital paramagnetic term where we can sort of classically rationalize it, that the electrons are moving, it's a moving charge and it's interacting with the field. The diamagnetic term is not that straightforward in that sense, but you can still have an analogy. So you can think of it like this, that the field, the B, it induces a precession of the electrons about the field. Okay, and this precession generates an induced magnetic moment, and this induced magnetic moment interacts with the field and raises the energy of the system. So while the orbital paramagnetic term is simply the interaction of a dipole created by a moving charge. So you can so the orbital angular momentum you can think of as a dipole moment generated by the circular or whatever motion of the electrons. The diamagnetic term comes from a precession of the electrons about the field. Okay, so that is if you want to think about it in classical terms. But like in quantum mechanics, it is not always necessary. I mean, just mathematically looking at the fact that this is positive and this is negative, and that will suffice for actually solving things. But if you want to really understand physically, then maybe you have to think of all these classical analogies. Okay. So, okay, this also tells you that the diamagnetic term is larger for larger molecules and smaller for smaller molecules. Okay. Now, I want to show you some examples the of what happens when you place a molecule in a field. So I will just stop sharing this screen and go over to my laptop. Okay, this one. Okay. So I hope you all can still hear me. You all can still hear me?
Yes, ma'am.
Okay. And you can see the screen where I'm trying to show you.
Yes, ma'am. That's
Yeah, okay. Okay. So let's see. So this is the spectrum of the carbon atom subject to a uniform magnetic field. Okay. You can consider this to be the z direction magnetic field. Okay. So the carbon atom has a triplet p ground state. So it has two electrons in the p orbitals, two p orbitals. And so the ground state here is that is this one. So the blue circles. So this is the zero field, and the strengths are in atomic units. So because you have three p orbitals, you see, as soon as I switch on the field, it splits into three, and you have a net lowering of the energy. So the carbon atom is uh, 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 so this here actually the spin interaction is also included. Okay, so this is an RPA based on the unrestricted Hartree Fock. So the because this is a triplet system, initially all states. So here these three states are triplet. So because of the spin interaction, which is always paramagnetic, like I said, the energies will be lower. So all three possible p states are lowered in energy because of the spin interaction. Then the lowest, the blue state is the one with the electron in the p minus 1 orbital. So p minus 1 and p 0 probably. Then that is the lowest. Okay, so here both the spin interaction and the orbital interaction are lowering the energy for the blue line. For the green line, the orbital interaction is neutral. It's coming from the P0 orbital, but the spin interaction is there, so it is getting lowered. Then for the P plus 1, so that then that raises the energy, and only the spin interaction is lowering it, so the yellow is more shallow. Fine. Then what happens? Then as the field strength increases, you see the a square term starts dominating the a term. Like you always know, the square term eventually takes over as you increase the value of the perturbation. So then this lowering is cancelled by the diamagnetic term, and the energy starts increasing again. So that happens first for the yellow line, because that was the shallowest, then the green, and the blue has not yet turned, but it will also eventually turn. So up to 1 atomic unit, the blue line has not yet turned. And this fact that the diamagnetic term eventually takes over, and the energies of all electronic states eventually start increasing with field, that is called the quadratic Zeeman effect. Okay? And this will happen for all states and all molecules eventually, but the strength of field at which it occurs, this will differ. So this is one thing. So these are the P states. Now let's look at an S state. So this square, black line over here, that is a quintet S state. I guess it's called a quintet. Yes, 5. So spin multiplicity 2s plus 1 equal to 5. If, for that state, there is no orbital interaction. It's only one state. There is no degeneracy, so it does not split, and it has a high spin multiplicity, so it has a strong spin Zeeman interaction, so it gets lowered in energy. Okay, and at one point around 0.2 atomic units of field, it even crosses the original zero field ground state. So then so at field strength of 0.2 to about 0.5, the quintet S state becomes the ground state. So magnetic fields can also change the ground state of the system. Okay. So when you actually plot states against fields, it is dangerous to say I'm plotting the ground state or the excited state, because these crossings keep occurring. And as you can see, the higher in energy you go, then there are many, many more crossings. Okay. So this is something you have to keep in mind if you're plotting electronic states against magnetic fields. Fine. So that was about the S1. And then eventually, after about, I don't know, 0.52 or something, then this green line becomes the ground state. This green line is the quintet F state. So why is the quintet F state having a higher slope than the black one? That's because the F orbitals also have a angular momentum. So here we have only plotted one F state, but of course there are many more F states. So you just plotted one, the lowest one here. So this would be the one with where the orbital involved is F with quantum number -3. So that would be the lowest F state, and eventually that becomes the ground state. And if but look at this at the zero field. It's a really high excited state. So it's like 1, 2, 3, 4, 5, 1. So no, so ground, then 1, 2, 3, 4, 5. So it's the fifth excited state. But when your field strength is about point a little more than zero point 0.5, it has become the ground state. So these in magnetic fields, these crisscrossings are very very large, and often it's difficult to know which one is the ground state at what point. So normally, most studies, they just focus on the zero field ground state. So when they're talking about ground, excited state, etc., in a field, uh, the ordering of the states is as they were in the zero field situation. Okay, so this is one thing. If you did not consider the spin, then of course you would have seen that uh, this triplet P, for example, that would have also turned diamagnetic from the very beginning because there was nothing to lower it. Okay. The this is there anything else I wanted to say? Okay, one more thing. So for that, I need to show you some molecule. Okay, yeah, one more thing. So in a molecule, so in an atom, there is no problem. But in a molecule, the geometry of the molecule, or the equilibrium geometry of the molecule, which is the geometry at which the molecule has lowest energy, this is typically frozen at the zero field geometry. But ideally, if you wanted to plot a proper state energy versus field, you should have optimized the geometry at every field. So that would have been the ideal situation. And then you calculate the energy states. But the problem with that is, firstly, it's expensive to do this, and two, it will become impossible to track the states. So the molecule may twist or look entirely different in the field if you let it optimize its geometry, and then even the symmetry point group of that molecule can change, and then course the end then trying to find out which electronic state corresponds to which zero field state, that is, well, not only is it an impossible task, I think that there is no correspondence. You cannot, it's, it doesn't transition smoothly. So this is an issue you have to keep in mind. This is something that people uh, will ask you if you're presenting anything related to molecules and magnetic fields. That what about the geometry? So, so then you have to justify saying that we fix everything at the zero field optimized geometry, because otherwise there is no correspondence between electronic states at one field and electronic states at another field anyway. So then it's an impossible thing to plot anything. Okay. Then you can only present single point values, that at this field I have these electronic states. You cannot track it across a range of fields. So that is the other thing. Anything else? No. Okay. I think that is it for today. So, do you all have any questions?
No, ma'am.
No. Is it becoming too much or too dense? Or is it okay?
Stephen, you can come in.
It